2016, Paper 1, Question 1, Complex Numbers. So in Question 1A here, we were told that -4 plus 3 is a root of the equation. And we're told that the coefficients of the complex quadratic equation here is A, B, C are all real numbers. And we have to, first of all, write down the other root. So the first thing we have to say is that we are told that the coefficients A, B, and C are all elements of the real number. And therefore, what that implies is that the roots occur in a conjugate pair. So if the roots occur in a conjugate pair, well then that implies that the conjugate of -4 plus 3i is also a root. And the conjugate of -4 plus 3i is -4 minus 3i. In other words, we change the sign of the imaginary part. So -4 minus 3i is also a root. So a nice and easy start to that question. And there's only 5 marks going for that. So if we said conjugate pair, you'd probably get 2 marks. And if we obviously state then what the conjugate is, we get our full 5 marks. So B then, totally separate question, is asking us to use De Moivre's theorem to express 1 plus I to the power of 8. And again, we have to do that in its simplest form. So simplest form meaning Cartesian form or rectangular form, whichever you prefer to call it. So here we have 1 plus I raised to the power of 8 means we're going to take the complex number and we're going to multiply it by itself 8 times. So of course, De Moivre's theorem is a nice, easy, simple way of doing that. So in order to use De Moivre's theorem, we always have to write our complex number in polar form first. So before we write it in polar form, we're going to need the modulus and we're going to need the angle. So of course, to find those, we're going to sketch the Argand diagram to make sure that we are in the correct quadrant. So 1 plus 1i means I'm going out a distance of 1 on the real axis and up a distance of 1i on the imaginary axis. So this is our real axis and our imaginary axis. So if I'm going out 1 and up 1, then that's my complex number there, plotted. Then the distance to the origin is my modulus. If I drop a line down, I'm making an angle theta with respect to the x-axis. So what I have done is I have gone up 1 and out 1. So therefore the opposite of my right angle triangle is 1 and the adjacent in my right angle triangle is also 1. So using Pythagoras, we're going to find the modulus. So in other words, modulus, which is also equal to OR. So OR can be found by getting the square root of a squared plus b squared, or applying Pythagoras. So we have the square root of 1 squared plus 1 squared, which is the square root of 1 plus 1, which in other words is root 2. And then our angle, so the argument of z, which is theta, can be found using tan theta, which is the opposite over the adjacent. So we have tan theta is equal to 1 over 1. So in other words, tan theta is equal to 1. So theta is equal to tan inverse of 1, which is of course 45 degrees. So again, you're either working in degrees or you're working in radians. So I'm going to stick with radians. But if you want to use degrees, that's perfectly acceptable too. It's always just important to be able to work with our radians. So important to check what quadrant do we lie in, and we can see that we are in the first quadrant. So therefore this is our angle. So now we're going to write this in polar form next. So when writing our complex number in polar form, it's z is equal to or times cos theta plus I sine theta. So therefore, if we sub in what we've just found there, our modulus was root 2, and the angle in radians was pi over 4. And if you were writing that in degrees, then you'd have root 2 cos 45 degrees plus I sine 45 degrees. So now we have our complex number. We have to take that and multiply it by itself 8 times. So in other words, we're going to use de Moivre. And de Moivre is saying that if we take the complex number and multiply it by itself a repeated number of times, then we can raise the modulus to the power and multiply the angle by the power. So what we have here is z is equal to root 2 times cos pi over 4 plus I sine pi over 4. And we wanted to raise it to the power of 8. So that means I'm taking all of that and I'm multiplying it by itself 8 times. So by using de Moivre then we're saying root 2 raised to the power of 8 and multiply pi over 4 by 8. So that simplifies down to give us root 2 by itself 8 times, which is 16. And 8 times pi over 4 gives us 2 pi. So again, either using our calculators in radians, or else we're using page 13 of our maths tables, because that's a nice special angle. So I always like to use my maths tables. Then that simplifies down to give me cos 2 pi, which is 1, and sine 2 pi, which is 0. So therefore, 1 plus I raised to the power of 8 is the same as 16 plus 0i. So we had 10 marks going for that. And it was broken down into 3 parts. So we had 0, 3, 7, and 10. So getting our modulus and our angle, writing it in polar form, and applying de Moivre's theorem. So in C we were told that 1 plus I is a root of the equation, so that means that it satisfies this quadratic. And we're asked to find the other root in the form of m plus ni, where m and n are elements of the real numbers. So the first thing that we should note here is that the coefficients of the quadratic here, so the coefficients a, b, and c, are not real, because we have an I here in front of the Z. So therefore, the roots are not going to be a conjugate pair. Okay, so it's important not to make the mistake of just automatically looking at that and going, oh, it's always the conjugate. It's not always the conjugate. We have to always check, are the coefficients of Z squared, the coefficients of Z, and the constant, are they real numbers? And of course, C has an I in it and B has an I in it. So there's 2 approaches to this. You can take it and say that A, the coefficient of Z squared, is 1. B, the coefficient of Z is minus 2 plus I. And C, the constant is 3 minus I. And you can use your minus B formula. And solve for Z. And you'll get 2 roots. One will be 1 plus I, and the other will be the second root. The other approach is to remember that we have Z squared minus Z times the sum of the roots plus the product of the roots is equal to 0, is how we form our quadratic. So if we look at that and we compare it to the quadratic that we've been given, then what we can see is that the sum of the roots must be equal to minus 2 plus I. But of course, if one of the roots is 1 plus I, and if we call the other root a plus bi, then they must sum to give me minus 2, which is plus 2, minus I. And of course, then if I get a plus bi on its own there, well, that would be 2 minus I. And if I subtract 1 plus I from both sides, I get minus 1 minus I. And therefore, that gives me the second root must be 1 minus 2i. So that's a nice, simple way of doing it. But of course, we can use the minus b formula either. So both approaches, full marks. That's our second root. So there was 10 marks going for that, and that was 0, 3, 7 or 10 for the breakdown.